we propose a systematic redesign of 3DGS densification. To select Gaussians to densify, we sample training views and compute per pixel saliency. A scoring function, f, combines gradient, saliency, and primitive properties into a per Gaussian score SG. The addition of new Gaussians follows a predictable schedule, assigning higher likelihood of replicating Gaussians that achieve higher score. Additionally, we follow a growth curve that mimics 3DGS behavior and can be fitted to yield any desired model size after training. Our new densification approach, combined with our optimizations on backpropagation, yields 5 times faster convergence speed without significant degradation in quality. To correctly propagate the gradients from the pixels into the Gaussians, we need to evaluate some per pixel per Gaussian values. These per pixel per Gaussian values can be imagined as a Gaussian pixel state table as shown here. We will now explain our approach for gradient backpropagation. We propose to parallelize over the 2D Gaussian splats. As shown in the figure on top right, this does not involve gradients being written to the same locations, thus eliminating the need for repeated atomic operations. However, this parallelization is not trivial. The evaluation of a single pixel Gaussian state requires information passing from either the Gaussian ahead of it or before it in the sorted list. Since 3DGS performed a sorted list traversal, this information was easily passed through the iterations. For us, an entire column representing a Gaussian requires information passed from either the previous or the next column. Since these states are already being generated during the forward pass, we solve the problem by sampling and storing the pixel states for every 30-second Gaussian in the sorted list. We parallelize the backward pass over the 2D splats such that a bucket of 32 Gaussians gets scheduled as a warp of size 32 where each thread deals with a single splat. For each warp, the first thread always reads the stored sample state for the pixels and processes it to accumulate the pixel's gradient contribution towards the Gaussian. It then passes the information to the next thread cheaply using intra-warp shuffling instructions. The threads once again process their states to accumulate the gradient contribution of their respective pixel into the Gaussian. This process continues. Each thread keeps accumulating the gradient contribution of the pixels in the tile. At the end, the threads stop when the entire pixel Gaussian state table is traversed and the gradients have been correctly accumulated. Due to 256 pixels per tile and 32 threads per warp, every thread spends 90% of its iterations processing gradients and only 10% of its iterations waiting. Considering a complete elimination of repetitive atomics and a higher degree of parallelism, this small trade-off is highly beneficial.